Hi class, welcome to Unit 4, Lesson 2. Diffraction of water waves is today's topic. So today's learning goal will be you'll be able to demonstrate understanding of diffraction of water waves and sound. And I know I have achieved these goals if I can describe in detail diffraction of water waves and sound, investigate the effect of wavelength and width of aperture on diffraction, solve problems related to diffraction, and apply learning to daily life problems. Diffraction is the bending effect on a wave's direction as it passes through an opening or an obstacle. Periodic straight wavefronts in a ripple tank travel in straight lines as long as the depth of the water is constant and the water is free of obstacles. But if the waves pass by a sharp edge of an obstacle or through a small opening or aperture in an obstacle, the waves spread out, causing diffraction. How much the waves are diffracted in opening a barrier depends on both their wavelength and the size of the opening. So as you can see here, we have some nice uniform ripple tank waves with incident ray this way, and they're all fine, and these continue like normal. But when they hit the sharp edge of an obstacle, notice this diffraction and bending around the obstacle. We have diffraction. And here's some really cool pictures of experiments in ripple tanks with different types of openings. And so we talked about some with obstacles and bending around the obstacles. So we have this one where we have a bending of both sides. So we have bending here and into here, and kind of what goes on. Notice how they kind of come together and make this kind of interesting squiggle inward convex shape. And this is a zoomed in version of it. You can see that it's an interesting shape here because of the diffraction of the two sides bending into each other. And we can also have it not just near a barrier. We talked about a aperture or an opening in an obstacle. And so here we have a barrier hole, and the waves experience diffraction with this opening, and they make this interesting outward radial waves pattern, which is also considered diffraction through the slit or the aperture. And we have the same thing going on here, just from not an aerial view, but from the side view. So we can see the crests and troughs of these uniform waves come through the opening and come out radially outward from the diffraction. So we said diffraction depends on wavelength. And so explicitly, shorter wavelengths are diffracted slightly, while longer wavelengths are diffracted much greater by the same edge or opening. So we can see here, short wavelengths, kind of what we had in the first example, short diffraction, and by the same barrier, longer wavelengths, we get much more diffraction. And this also follows true for not just edge obstacles, but the aperture, like our holes in the boundary obstacles. So we have, as the wavelength increases, A is shortest wavelength, C is longer wavelength. Notice the amount of diffraction is increasing as well. And the width specifically in this picture is not changing. W of the aperture is the same in all pictures. So strictly in this diagram, the changing wavelength is what's going on because W is constant. That's not to say that the width of an aperture doesn't have an effect, because it does actually. So when we keep the other variable, when we keep our wavelength fixed and change the size of the aperture, we find that the amount of diffraction increases as the size of the aperture decreases. So, and in both instances, if the waves are to be strongly diffracted, they must pass through an opening of width comparable to their wavelength or smaller. So we have the situation of wavelength less than, or width of the aperture is less than or equal to the wavelength, or equivalently comparing the ratio of wavelength to aperture width. If we have that greater than 1, then we can experience some strong diffraction. So to push this point into more perspective, in A and B, similar wavelengths are diffracted more through a smaller opening, whereas in B and C, the openings are the same size, but the wavelengths are shorter, and in C, there is less diffraction. This means that if the wavelength is very small, a very narrow aperture has to go with it in order to produce significant diffraction. And this is just telling us, this is showing the same thing, that this ratio, if our wavelength is very small, so our denominator is much smaller, and we have a giant wavelength that's going more and more positive. This is going down and positive. This is going to approach 0, really, right? So we don't want we're not going to experience diffraction like that. But if we if we keep lambda, say, is small, but we bring down the wavelength to smaller and smaller, then this ratio all of a sudden approaches positive infinity, which is greater than or equal to 1. So that's why that if our wavelength is very small, we need a very narrow aperture to go with it to produce diffraction, or significant diffraction. So we see that in A and B here, right? With the same wavelength, if we decrease the aperture, we get much more diffraction. But if we go this way and increase the aperture for the same wavelength, then we're going to get much less diffraction. So sound is one of the most clear examples of diffraction. So in sound waves, the sounds of a classroom can be heard through an open door, even though the students are out of sight and behind a wall. Sound waves are diffracted around the corner of the doorway primarily because they have long wavelengths. And this is relative to the width of the opening, because as we saw, they both play a role with that ratio, right? And so if a sound system is operating in the room, its low frequencies, the long wavelengths, are diffracted around the corner more than are its higher frequencies, because they have shorter wavelengths. And so the low frequencies like beat and lower sound frequencies, you can hear them more clearly from if you're standing in the hallway versus maybe crash cymbal is high frequency, so you might not hear that, but you could hear beats and bass. Bass is another one, so thanks to diffraction. So sound wave diffraction is explaining why we can hear sound around corners, and so diffraction of sound around our heads makes hearers misjudge locations of the sound sources, and so notice the diffraction here, misjudging where it's coming from if they're all the way down here, thanks to diffraction. And that's the end of the lesson for today.